first of all, thanks for inviting me here. And thanks very much for the Franklin Fetzer Institute for funding our small group as a startup group. When I look at the numbers that we've got and we compare them with the people at Vienna University, we are real amateurs in that sense. Now, the next thing I've got to do is I've got to apologize because I've changed my title. And the reason being that after writing a talk, I realized I could not get it done in the time. So rather than go in that area, which is a bit technical, I'm going to give a heuristic introduction to the ideas and introduce my experimental colleagues. Particular, I want to introduce Robert Flack and Peter Barker. It was really Robert Flack who came up to me one day in University College and said, "Why don't we work together?" And I said, "Well, what are we going to work on?" And the weak values that Aronoff and Lev had put out seemed to be a good thing to try and understand what the devil was going on with that. And then Bob actually said, "Okay, let's go." And we went to see Marcus Ant. And Marcus said, "Well, you've got someone at UCL just under in the basement laboratory who knows all about this." And so we got introduced to Peter Barker, who was actually in the same institute, and we didn't know he was there. So this started the whole exercise. And on there you'll see one interloper, who I must mention, and he'll be talking later on. And that's my good friend, Maurice de Gosson. Because without Maurice, I would have known no mathematics at all. So all the errors are mine, all the things that are correct are his. Okay, so let me start then. I am now going to be totally different to everybody else. Having years spent talking about Bohmian, not quite Bohmian mechanics, but about the same sort of subject, I now find everybody else is talking about it, and I'm talking about something completely different. What I want to talk about is really something which I started working with David Bohm in the 60s. And that was that he didn't believe his interpretation at that stage anymore. And he'd moved on, and we had at Birkbeck Roger Penrose. And Roger Penrose was very interested in the idea that we shouldn't be doing quantum mechanics in classical space-time, but we should be getting space-time emerging from something deeper. This is one of the points that you raised in your introductory talk. I thought I was a bit way out, but when you said that, I was very pleased, because that meant I could legitimately talk about these ideas. Okay, so the idea is that we're not going to talk about material objects moving in space and time. We're going to talk about process. Now, the trouble with talking about process is you're obviously going to say, well, what the hell do you mean? So let me try to build up this idea of structure process. And I thought I'd build it up by showing you this man. I don't know how many people have actually seen Anthony Gormley's subject called the quantum cloud. Well, according to the information I've received, that he was actually inspired by the work of David Bohm and myself to actually build this structure so that we don't have a man appearing as a man as such, but a man is emerging out of a structure process. In fact, what I do know as fact is that I actually appeared on a radio discussion with Anthony before the thing was actually built. And I think this directs you to the type of thing I'm going to be talking about. Of course, here, this is only a metaphor. The rods of which this is built out are actually material process and therefore very rigid and so on. What we've got to do is to somehow find a mathematical description of these ideas. And what we came up with, and I know you don't like this, Lev, but please, let's go on. It really comes out of the algebraic approach. Now, why did I mention Penrose to begin with? Because when I was working, when I used to go and listen to Roger at Birkbeck in the 60s, he was developing his ideas on twistors. And I wondered what the hell these twistors were. There were symbols, the left, right, and center. Until I didn't understand it until I actually got hold of the structure of Clifford algebras and I saw how it emerged there. And this sort of got me thinking about Clifford algebras. And in particular in the sense of describing structure process. Okay, now what I want to do very quickly in this talk is to show how the standard formalism and classical mechanics emerge from this structure, heuristically, not in mathematical detail because I don't have time. And then I want to focus on the weak values of the momentum operator and show that it has a long history, the weak value of the momentum operator. It usually goes under the name of, originally under the name of local momentum, and this is particularly brought out in Michael Berry's paper, The 5 Momenta. But in that 5 momenta, he doesn't mention the Bohm momentum, he doesn't mention the guidance condition, but as you will see, these are exactly the same expression for the local momentum. So we're really talking about, if you don't want those other fancy terms, we're talking about local momentum. And this whole structure can fit very neatly into a non-commutative phase space. And the aim of our experimental group is to actually do experiments to see if we can tease out what this structure is and what's important in this structure, what isn't important in this structure. Okay, so that's the general idea. Now, what do we mean by structure process? I'm going to come off this balcony because I'm going to fall if I'm not careful. Don't mind me standing here, do you? Okay, so how do we deal with this? Well, the first place is just look at the particular process of becoming and give it an arrow like that. And then we're looking at being as a special case of becoming. So our objects are going to be created out of stationary states, if you like, processes that keep repeating into each other. And the important there is the idea of the idempotent, which is just A times A squared is equal to A. And that's something which is, in terms of process, keeps repeating itself on and on and on, not by being stationary. Okay. So I'm going to deal with little objects like that. Now, why do I think or where did I get this idea of the idempotent being the most important thing? I got it from Eddington, actually, way back. He said, he was discussing what is a particle. Is it a metaphysical lump of something? Or is it a structural concept of existence which is represented by this idempotent symbol? And it's this thing that I've been developing in this particular way of looking at things. And when I say I've been developing it, David Bohm and I were discussing these things, so it's not solely due to me. The presentation is mine, but it came from discussions with David Bohm. And it's very much related to his implicate order. Okay, now the way to discuss this is in terms of the groupoid, and that's why I had tangent groupoids in my original title. And what is a groupoid? A groupoid is a very primitive object which consists of 2 processes, and then the question is, how do you define the order of succession when you've got 2 isolated processes? Well, the groupoid does it for you. It says that if you think of J as the target of that process, as you think of J prime as the source of the other process, when the target agrees with the source, then you have this multiplication law. And if you have a look at that multiplication law, it looks very much like matrix mechanics. And of course, that's what Jordan actually said to Heisenberg, look, what you're dealing with is really matrix mechanics. But that's the representation of the algebras that I think lie at the base of quantum mechanics. And I just want to show that there is a rigorous mathematics behind all of this, because I'm going to be hand-waving from now on. And it's in the monoidal category, and there's a very good paper by Samson Obronsky and Bob Koch, who does quantum mechanics, kindergarten quantum mechanics from the categorical point of view. And it fits in very nicely with the general philosophy that I'm using here. Okay, just let me quickly remind you that where I'm going back, I really am going back in time. And I know I'm a pretty ancient guy, but I think it's a good lesson to go back and see where we started. And we started with the Heisenberg-Born Jordan mechanics. And remember, Heisenberg was trying to understand the Rydberg combination. And what he found was that by using these groupoids, he didn't know they were groupoids in those days, writing them as exponential, you've actually got the combination principle here. And of course, we understand that nowadays with the simple Bohr theory. But more than that, what this actually led Heisenberg to was the fact that you've got non-commutativity behind here, and immediately you get the Heisenberg equation of motion. So this was all in the 1925s, and there's nowhere is Schrödinger in this picture at all, yet. Okay, so then notice that we've written this, this Q, what was the position, as a matrix, as a complex matrix, and we think of this as a phase angle. And so a lot of the work, particularly the work that Mike Berry does on his super oscillations, is always using the phase angle. But when you want to put in the spin and relativity, where's, I don't know where he's gone, over there somewhere. When you put in spin, you've got to generalize this idea, which I don't think you do, but you can correct me if I'm wrong. And then what you find is that you can generalize this idea and make this phase a matrix. And it's the matrix there, U. And that matrix actually contains all the information about the spin. It also contains information about the relativistic side of things. And just to quickly show how it works in terms of matrix representations, this is the Pauli spin matrix. This is the object that one should be using in the algebraic approach. And there's a relation between the components of the wave function, and it's all embedded in the actual algebraic structure. And then you can do the Dirac theory that way. And notice that you've got elements of the algebra which are, as it were, outside of space and time. All the coefficients are functions of x, but not sigma 1, sigma 2, and so on. And then you can even put Schrödinger's equation in that form. Normally, we look at them in terms of column vectors, but all of these embed inside this Clifford algebra, and what we've got on the top there is Penrose's twistors. And you can actually do the Dirac equation. You can then go to the non-relativistic limit, and you get the Pauli equation in there. You then go down into the spinless limit, and you've got the Schrödinger equation. So it all fits in very nicely into that mathematical structure. And you're leaving behind the approaches that we've all been talking about here. Okay, so now let's have a look. Is this completely different from the bracket notation? No. The bracket notation is absolutely beautiful for this, because what we want to look at are the outer products, not the inner products. And the outer product is, how do I go from I, how do I go from J to I? In there I've got my idempotent. What we always concentrate on, and the last lecture was very much reminding me we were all concentrating on this, but I look at this as a transition probability amplitude, not as a wave function. It's the probability amplitude of finding the process I given the process J. And that's what I wake up to find, that what Yakir and Lev were doing, were really giving those a different name. So they're doing exactly the same as I had been doing for a long time. Okay, so the wave function is a transition probability amplitude, and it is not a physical wave. Now then, can I get a little bit closer to what Yakir was talking about? Well, the way I do it is a symbolic way, is that I actually pull apart. Sorry, I'm an amateur at this game. Why should I be an amateur after all this time? Look, if you pull this apart, what you've got is a left ideal and a right ideal. And these are structures which replace the wave function. They've got all the information, but they're in the algebra itself. They're not in the Hilbert space. The Hilbert space is a representation of them. This is all encoded in the algebra itself. And then the basic description element I use is essentially a two-point or a two-state density matrix. Now, why am I doing this? Because we want to include spin. And the way you include spin is, if you look at this, you see I introduced that idempotent earlier on. And there it is sitting in there. What the idempotent does is actually breaks the symmetry of the rotational group here. And that gives you, and these are all orthogonal Clifford algebras, whereas the Dirac picks out the time axis. So although it's relativistically invariant, you still pick out rest frames. And you work everything out in terms of that. And in fact, even Schrödinger can be put in that. And I spent a few years trying to understand where the idempotent was in the symplectic Clifford algebra. Okay, so that's the background. Now, the question is, where does probability come in? Where does statistics come in on this thing? Well, it comes in, once again, I'm afraid this is all relying on the mathematics. You can say to me, rubbish, because it's all mathematics, but it's the mathematics which we use in different ways in everyday language, in physics anyway. What we find is there's a very deep theorem, it was called in linear algebra, which says that if you sandwich any element between two idempotents, you find that you get the expectation, what turns out to be the expectation value, multiplied by the idempotent. So it's already embedded in the algebra. Okay, so how do you prove that? I asked Lou Kaufman, he said, well, it's that picture there. Just join up the lines and you'll find that you can then pull them apart. But if you don't like to do that, just do it this way, put it between bras and kets, and you see immediately that you've got your expectation value in there. So it's not very million miles away, and you can do diagrams, and that's what really Bob Koch told me, re-emphasized what I was doing and made me feel very comfortable because he was getting it from his monoidal category theory. So it's not just pictures for the sake of pictures. Okay. Now, what about the weak values? How do the weak values fit into that? Well, we've got our oh dear, sorry. We've got our expectation value as a trace of this with this density matrix. We then notice that here's the weak value which people have been talking about. Now, how do we analyze that? I want to say that this value is actually a transition probability amplitude. And it's important to get that idea in. Then, if you have it as a transition probability amplitude, you divorce it from values, namely eigenvalues. And what you find is, you see, why do you get 100? Well, look, there's the eigenvalue of this particular operator. I'm looking at it, and look, it's multiplied by these objects. So, if I choose these objects to be 1 minus, I've got a two-state system, eigenvalue minus 1 plus 1. I've got the D's, look, minus 99 and 101, see, and I find that the weak value is exactly 100. So it's this weighting function. I would like to say it's got nothing to do with eigenvalues, but it does. But they're eigenvalues which are weighted in this way. And if you think of them in terms of transition probability amplitudes, then I feel, for me, it's much clearer. Now, how do I relate this to the standard approach? Well, I use exactly the same relation, only instead of making that substitution, I make this substitution. And that'll give me the standard result. So that shows how the standard result comes out. Okay, now then, is it reasonable, those coefficients I've chosen? And the answer is yes, and this goes back to this particular page. I think I've seen this picture a couple of times already. It's the duck experiment, which really kicked myself and Robert Flack off. And if you have a look at that, we've got the tan theta is alpha by 2, or alpha is that angle, and it's very easy to make that infinite if you want to. And of course, this experiment, which was discussed earlier on this morning, these particular curves, and these actually show you that you get your infinity there. Now, what Rob Flack and Vincenzo Monachella are going to do is, instead of using neutrons, they're going to use excited helium atoms. And I'll leave Bob to actually tell in his talk exactly how far he's got with that. But that's where this particular experiment fits into that general background. Okay, now let's go to the weak momentum. And then this actually, it's just the local momentum. As I say, it's got a very long history. And in fact, it goes back, I've traced it back at least to London's paper in 1945. But he has a reference to Landau, and I thought, I'm not going any further back. I knew about this Hirschfeld, Christoph, and Polk paper in 1974, And in there, you'll notice is the osmotic velocity already. And he's actually got calculations for the osmotic velocity. Did you know that? Oh, sorry, I thought I'd found something. But to have a look at the...
In some Bohmian papers, yeah.
Oh, it's probably mine. Okay. Yeah, okay. Yeah, yeah, okay, good. Because, you know, it was so far in the past. It's ancient history even to me. Anyway, so, and to have a look at these two velocities, this lovely paper by Bloch, who actually talked earlier on, and this was exactly what I worked out, and to find a paper where he's actually drawn the osmotic velocity was very nice. And even in that paper, and has got how the quantum potential appears out of this velocity, and that's a lovely paper that you have bringing that out very clearly. So if people want to read about that, read Gerhard's paper, which is it's a beautiful paper. Okay, so now I want to just put in one thing about stationary states, because one of the things that gave David Bohm absolute jip was Einstein objecting to the stationary states. Because in the stationary states, if you just take notice of the Bohmian momentum or the local momentum, it's always zero. Because the wave functions are always except for the energy part. And then what happens was in that paper, we had to explain that the quantum potential was where all the energy was stored. And in fact, you can make a nice little picture of that. But what I missed, and what a lot of people may have missed, is the fact that the osmotic velocity is still present. That's what you point out, it's still there. So that actually what you've got is this additional velocity. It's the sort of the basis of the hydrodynamical model, but why hydrodynamics for a single particle? That's the puzzle. Or is it just buried in the non-commutative mathematics, which is what I believe it is? But that's another story. Okay, so why don't we see this osmotic velocity in the normal quantum mechanics? And we don't see it because if you, what we do in quantum mechanics, is we always integrate the local velocity over all of space. And once you do that, you find this is zero. And this is George Mackey pointed this out in his Mathematical Foundations of Quantum Mechanics a long time ago. But what we can see from the work that Gerard and the earlier people did was if you work out the weak value of the kinetic energy, you find that it actually contains the quantum potential. So if we could measure the weak value of the kinetic energy, we will actually be able to put a number to this quantum potential. And it's one of the things we're keeping in mind with the experiments we're doing. Okay, so how does classical mechanics emerge from this? Well, very simply, just go back and do what David Bohm did right at the beginning and simply write the wave function in terms of its two real components. And then what you find is that you get the imaginary part is just the conservation of probability in the usual way, and we get the real part is just the classical Hamilton-Jacobi equation plus this extra term which everybody finds revolting, or they did in the early days. For some reason, they say shouldn't take any notice of it. And then, of course, what you see is that if you can neglect the quantum potential relative to, say, just the kinetic energy, you find you get classical physics out. So classical physics is already embedded in this. And if you do the algebraic properties, if you do the algebraic structure properly, you see this is just deformation quantization I'm talking about. And then what you find is, I thought I'd say, okay, people would wonder, you know, are there any situations where you can actually find the quantum potential changing with time? And the answer is yes. I was reading a paper about the inflationary universe. You remember the whole idea about making inflation, and then it satisfies some criterion that I forget what it was, I think uniformity. And what I did was to say, all right, let me take that, the potential they're using, which is an upside-down harmonic potential, and I'll sit a little Gaussian wave packet on the top there. And I'll let the particle be on the right-hand side, and let it go running down the particle, down the potential. And what you find is you can calculate the quantum potential, the classical trajectory, quantum trajectory, beg your pardon. And I'm always putting trajectories in quotes in my story. Always putting it in quotes. What you find is that here is the quantum version of it. And if you have the corresponding classical version, it's like that. And you can actually see the two merging continuously in this limit when the classical kinetic energy, or sorry, just the kinetic energy dominates the whole thing. And so you've got a rather interesting situation that we've got a new sort of exchange of energy in this particular theory, where the kinetic energy and the quantum potential energy, the kinetic energy disappears and stores it in the quantum. It reminded me of an F1, I was watching it, I'm sorry, I'm an avid F1 supporter, and we have a KERS system there, which they brought in 2 years ago, and it's a kinetic energy retrieval system. And this is a classical kinetic energy retrieval system. Okay, now, so the real question is, and this is my final slide, the real question is, look, we've had this for donkeys, it seems donkey's years to me. And it was always ignored. All these trajectories are out there and people were saying they're meaningless, and blah, 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 blah. And I was wondering why. And then I saw this statement in Fritz London, this is 1945. The local mean velocity has no true quantum mechanical significance since it cannot be expressed as the expectation value of any linear operator. In other words, they're using that definition for what quantum mechanics should be. And anything that doesn't fit that definition must be rejected. What I was doing with David was to show that you don't have to stick with this linear. It's merely a representation of a much deeper structure, namely the algebraic structure. And what I was hoping to do was to show how it comes out of the tangent groupoid and how you could see it all, but that was too much for half an hour. Anyway, what's changed? Well, of course, it's Ephraim's Canadian group doing this work. Absolutely magnificent, has suddenly woken everybody up. It gave me a kick up the backside. Seeing those things there and saying, how the hell has he done this when it's not supposed to be possible to do it? And then finally, why I'm coming to this is that we are actually going to try to measure the local momentum using argon atoms. And at UCL, we have this group with Peter Barker, Pete Edmonds, and Joel Morley, who started earlier this year and are well on the way, and Peter will explain how far we've got so far and where we're going. Okay, thank you.